going to look at operations on functions. That is what you need to pay attention to if you're going to add, subtract, multiply, or divide functions. Here we have two rainbows and they're sort of parallel to each other. So you could consider one of the rainbows as a constant function added to the other rainbow. To add functions, you are stacking two functions together to create a resulting sum. Here the green function is the sum of the square root of x plus 0.5 times 2 to the x. At x equals 2, you could see that the value on the green function is the square root of 2 added to the value on the blue function, which is our original exponential function. If you look at x equals 3, if I took the value of the exponential function and added it to the square root of 3, I will get the resulting function on the sum. And I could do that at any one of the x values. I just picked 2 and 3 because they were kind of nicely illustrated in the middle of the graph. So again, when you add functions, you literally are just adding the individual function values to create your resulting sum. And the domain will be the most restrictive of the functions that are being added. So in this case, the square root of x was the most restricted. We can only plug in 0 or positive values into the square root of x. The exponential function has all real numbers as its domain. But once I add them, the square root dictates the restrictions on the domain. So the domain of the resulting sum is x greater than or equal to 0. Again, I'm only able to plug 0 or positive values into the square root. We can see from this graph that the range is y is greater than 1/2. When you plug 0 into the square root of x, you get 0, but when you plug 0 into the exponential function, you get 0.5 times 2 to the 0, and that gives you 0.5 because it's 0.5 times 1. So the lowest value on the sum is 0.5, what you get when you plug in x equals 0. And then from there, you could get any value higher than 1/2. Here we're showing the result of taking the square root of x and subtracting 0.5 times 2 to the x. Notice that at x equals 3, the value of the resulting function has a difference of 0.5 times 2 to the 3rd from the square root function. So I've shifted the square root function down by the value of the exponential function. The domain is still x greater than or equal to 0 because of the square root restricting us to 0 or positive values. And the range in this case is y less than or equal to 0.025. 0.025 is the highest y value that we reach on the difference between these two. It's a little difficult to figure out that that's actually the maximum. I'm kind of just telling you that's what it is, and you can see from the graph that it does look like it's some value slightly above 0. In calculus class, you would learn how to analyze the function to figure out exactly what that maximum value is. But for the moment, I will just have you look at the graph and point out that the highest y value is slightly bigger than 0, and it turns out it's 0.025. You can also multiply functions. We're still working with the square root of x and the exponential function 0.5 times 2 to the x. Notice the notation. There's different notations on how to express that you're multiplying functions together. Here, when both functions were less than 1, notice that the resulting product is a value that's lower than both of the original function values because you're multiplying by something less than 1. When the function values individually were greater than 1, the resulting product is a value that's higher than both of the original functions. So the black graph is the product, So notice for values of x less than 1, the black graph is lower than the blue and the red graph, which are the original two graphs. But then for values greater than 1, the black graph is higher than the other two graphs. Functions can also be divided. So here we are dividing the exponential function by the square root. You also could have the square root being divided by the exponential function. One thing to pay attention to when you are dividing by functions is to see whether or not you've created a new restriction by the division. So earlier we were stating that our functions had domain x greater than or equal to 0, and that was because the square root of x could be 0 or any positive value. But for the function where we're dividing by the square root of x, you cannot divide by 0, so your domain gets restricted even further to be x greater than 0. You only can plug in positive values because you're no longer able to plug in 0 due to the division by 0. However, when you were dividing by the exponential functions are never equal to 0. And so our domain is still just restricted by the square root. So the domain of the square root of x being divided by 0.52 to the x is still x greater than or equal to 0. Notice too that when the exponential function was in the denominator, exponential functions become very large quickly. Like I don't have to plug in an x that's too large to get an exponential function value that's large. So notice the graph of that division is fairly quickly tapering off towards 0. Whereas when I was dividing by the square root of x, the square root of x stays relatively small related to the exponential function. And so its values are lower than the original exponential, but they're not tapering off so quickly like when we were dividing by the exponential function. Here we're emphasizing that the domain when you divide by the square root of x is further restricted to x greater than 0. We can no longer plug in 0. We're also showing that the original exponential function is this green graph, and when we divide by the square root of x, when the square root of x is greater than 1, notice the values of the quotient are lower than the original exponential function. However, when the values of the square root of x are less than 1 and I'm dividing by values less than 1 is going to make the value of your function higher. So my quotient is the blue graph, and for values of x less than 1, the values of the quotient are higher than the original exponential function. When the values of the square root of x are greater than 1, then the values of the quotient are lower than the original exponential function. So you kind of want to look at the blue graph and how it's comparing in terms of being greater than and then eventually less than the green graph. Aside from paying attention to domains and ranges, you also want to pay attention to the actual algebra of combining functions. So we'll look at some examples. We'll use f of x as the square root of 2x plus 10, and a second function g of x as x minus 4 squared minus 5. So the quantity x minus 4 is being squared, and then you're subtracting 5. And we'll look at the algebra when we add them, when we subtract, when we multiply, when we divide, and we will also compose the functions. So a composition of functions means you are using one function as the input for the other. So f and g of our exercise here are examples of composing functions. You're plugging a function inside of another function. Here we are adding the functions, and no surprise, You're just literally adding them. There really is no simplification that can be done when you're adding these two functions. The domain will be the domain of the most restrictive function. So the square root of 2x plus 10 is restricted in that you are not allowed to plug negative numbers in if you're defining it in the set of real numbers. So 2x plus 10 equals 0 when x is negative 5. If I plug in negative 5, the square root of 2x plus 10 would be 0. So the domain is x greater than or equal to negative 5. If I were subtracting, there's just a little bit of simplification. Notice if I'm subtracting g of x, you obtain minus the quantity x minus 4 squared, but then plus 5. You were subtracting 5, but now that you're subtracting g of x, you would be adding 5. And the domain is still the same restriction from the square root, x is greater than or equal to negative 5. For these two functions, when they are multiplied, again, there's no special simplification. You literally are just expressing the one function, square root of 2x plus 10, multiplying the second function. But notice that you do want to put parentheses around the entire parabola, x minus 4 squared minus 5. If you do not, you're really indicating that you are just multiplying by the x minus 4 squared, and from that expression you would be subtracting 5. So you need to put the parentheses around the entire parabola. The square root is still the most restrictive. We're still working with the same two functions, so the domain as it was with the sum and the difference is x greater than or equal to negative 5. Now if I were dividing the square root of 2x plus 10 by the parabola x minus 4 squared minus 5, there are two values that make the denominator 0. And so if I set x minus 4 squared minus 5 equal to 0, if I set the denominator equal to 0 and I solve, I get the square root of 5 plus 4 and negative square root of 5 plus 4. So those two values would make the denominator equal to 0. I would create division by 0. So those two values need to be removed from the domain of the quotient. So my domain of this quotient is still x greater than or equal to negative 5 because of the square root, but now that I put the parabola in the denominator, x cannot be the two 0 values of the parabola. So x cannot be square root of 5 plus 4 or negative square root of 5 plus 4. So this domain has a slight addition to the restrictions. You still have x greater than or equal to negative 5, but you also cannot have x equal to those two values that make the parabola 0. You can see where the square root of x plus 4 and minus square root of x plus 4 are on the graph. It is where those vertical sections are of the blue graph. I'm soaring to positive and negative infinity around those two values. You can also reverse the numerator and denominator and create a new function with the parabola in the numerator and the square root of 2x plus 10 in the denominator. When you do so, the domain of this quotient is x greater than negative 5. We no longer can plug in negative 5 because the denominator would equal 0. 2x plus 10 would equal 0. So the domain of this quotient is x strictly greater than negative 5. So notice in the graph, it is only appearing to the right of negative 5, and at negative 5, the graph appears to be soaring to infinity. As mentioned earlier, composed functions means that one function is being used as the input to another function. There are a couple different notations. One, literally, you're showing g of x as the input for function f. You also could use this other notation where you write f and then sort of a degree symbol. g of x, that's read f circle g, but it means this idea of composing g as the input to f. So g was our parabola, x minus 4 squared minus 5. So I am plugging that in for the variable in the square root function. So the square root function was the square root of 2 variable plus 10. So where the variable x was, I've replaced it with x minus 4 squared minus 5. Once again, I need those parentheses around the parabola. Now, in this case, we can clean things up a little bit. Distribute that 2. So I would multiply 2 by the x minus 4 squared, and then 2 times negative 5 is negative 10. And what do you know? Negative 10 plus 10 is 0. So the function simplifies down to the square root of 2 times the quantity x minus 4 squared. And I can distribute the square root over the product, and I would get the square root of 2. And be careful, the square root does kind of cancel the square, but when you squared x minus 4, it was always positive. So when you do analyze the square root of x minus 4 squared, you have to consider that the value of x minus 4 is only going to be positive because of the original square. So that function simplifies down to the square root of the absolute value of x minus 4. Now, if you graph the square root of 2 times the absolute value of x minus 4, there's no reason that you can't plug in values less than negative 5, and so that's why on Desmos we're seeing the graph graphed at negative 20 and negative 40 and negative 60. However, if you're really following the rules, if we started with the square root of 2x plus 10 and that parabola, the square root of 2x plus 10 was only defined for x greater than or equal to negative 5. So you can't really use values that you didn't have available to you in the first place. So because we started officially with the square root of 2x plus 10 as one of our functions, the domain of this composed function should really just be x greater than or equal to negative 5. We should not assume that you can plug in values less than negative 5. We could also compose the function in the other direction. We could use f as the input to g. So if you take the square root of 2x plus 10 and you replace the variable in the parabola with the square root of 2x plus 10, you end up with the function shown here. There's really no point in reducing it any further. It's about as cleaned up as it will be. Our domain is still x greater than or equal to negative 5 because of the restrictions on the original square root function of the square root of 2x plus 10. Sometimes it is worthwhile to clean up your results. The last examples we had, there really wasn't much algebra cleanup, but here we have an example where there is more purpose to cleaning up the algebra. We have the function 2 over x, and then a second function, x cubed minus 8. When I add them, I literally am just adding the functions together. I could leave it that way, but you might want to write it as a single rational expression. So the x cubed minus 8 needs a common denominator of x, hence the x cubed and the 8 need to be multiplied by x to the first power to keep balance the fact that you put a x in the denominator of the x cubed minus 8. So the new function becomes 2 plus x to the fourth minus 8x over x. If I multiply them, then 2 times x cubed minus 8 is in the numerator, and there's a single x in the denominator. So you might want to rewrite that as 2x cubed minus 16 divided by x. If I divide with f of x in the numerator and g of x in the denominator, notice that since 2 divided by x has an x in the denominator, it essentially creates another factor of x in the denominator. So the cleaned up result would be 2 divided by x to the 4th minus 8x. Reversing that quotient with f of x in the denominator, dividing is the same as multiplying by the reciprocal. So when I divide by 2 over x, it's essentially the same as multiplying by x in the numerator with a 2 in the denominator. Notice I end up with the reciprocal of the previous quotient. Here we have composed the two functions with which we have been working. If you use g as the input, notice that f, which was 2 over x, becomes 2 over x cubed minus 8. If you use f as the input, then x cubed minus 8 becomes 2 over x cubed minus 8, and you can simplify that to be 8 over x cubed minus 8 if you would like. So these are some examples of adding, subtracting, multiplying, dividing, and composing functions. We looked at how to pay attention to the domain and noticed when the domain was restricted due to what original functions we worked with, and we looked at some of the algebra simplification that can be done.